We are continuing with the work integral by going over multiple examples. This example has a few new wrinkles to it. For one thing, the curve, in this case, is a picture. You know, they don't spell it out. They don't parameterize it for us or anything like that. They just give us a picture. And the arrows mean the direction of the integral. When it's piecewise continuous like this, the total work is the arithmetic sum of the work over each continuous segment. So the total work will be the work from here to there, and then the work from here to there. So this has two segments. Another new thing is it's nice straight lines that are aligned with the axes. It's kind of an easy way to do those kind of problems. For this first leg, y is always 2, which means it's a constant, which means dy equals 0. And on this leg, x is a constant, meaning dx equals 0. So look at the integral here. Here was the problem given to us. On the first leg, dy was 0. So this whole thing goes away, and y was just 2. So the whole integral for the first leg is just, there's the integrand, just 2x plus 2 dx. And we're worried about where x goes, because that's what we integrate over. It goes from -1 to 2. So there's the first leg. On the second leg, dx equals 0. So this whole front term goes away, and x itself equals 2. So it'll be 2y dy. And y goes from 2 to 5. There's the second leg. Just take these two integrals normally and add them. Closed curves. That just means they come back on themselves, and you should have this symbology on the integral symbol when it's a closed curve. So here's an example. Evaluate this closed curve integral, and the curve is the closed triangle. It gives you the points of those triangles. From the origin to this point, then to this point, and then back to the origin. Might help you to draw it. First, identify what the f is in terms of a vector: y squared, z squared, x squared. Okay. Now we have to parameterize it ourselves this time. In every other case, it was pretty clear what the parameter was. Either it was given to you explicitly, or it was pretty easy, like x is a function of y. So here we have 3 straight legs, so we need to parameterize it. And for that, we need to go back, I think, one module in my course where we talked about lines, how to describe lines from points. And this is going to be 3 different legs. It's a triangle. Here to here, then from here to there, and then from here to there. 3 legs. The first and last legs are easy to parameterize because they go, one point is the origin. So the line going from here to there is pretty easy. I can just say it's t, 3t, 5t, and let t go from 0 to 1. I don't have to do too much thinking for that. And then dr is 1, 3, 5. F, wherever there's an x, I put in t. Wherever there's a y, I put in 3t. Wherever there's a z, I put in 5t. F dot dr is that, which simplifies to that. With x, it simplifies to just 89t squared. And t goes from 0 to 1. See how we parameterized that leg? That was easy because it went through an origin. The next leg is not so easy. It goes from 135 to 444. So remember, to describe a line, we needed a point and a direction. Well, for the point, we could use 1, 3, 5. For the direction, we've got to take that difference. 4, 4, 4 minus 1, 3, 5. 3, 1 minus 1. And then this was the way to parameterize using the parameterization method. We had 3 different ways to write the equations of a line. This is the one that gives you the function in the parameter t, each of x, y, and z. Remember, you might have to recall how to do that. But now we have, it's parameterized. The second leg is now parameterized in terms of t. T is going to go from 0 to 1 again. You might want to check it. T equals 0, I get 1, 3, 5. T equals 1, I get 4, 4. That works. So then dr equals 3, 1 minus 1. In F, make these substitutions. That, take the dot product, simplifies to this, and that is our integrand for that leg. T goes from 0 to 1. So that's leg 2. For leg 3, we can go back to the easy method through the origin and just say R is TTT because we're going from 4, 4, 4 to 0, 0, 0. And we'll say T goes from 4 to 0. DR is just 1, 1, 1. F, everywhere there's a T. Everywhere there's an X, Y, or Z, I replace it with T. So they're all T. So then that's the third leg, and the total, I just add up the 3 legs. So this second leg was really the hard part of this problem. It's a little tedious, I'll admit. I made my students know how to do that. In this example, you again have to come up with your own parameterization. This leg is easy. It's like the other drawing we did. Y is 0 and dy is 0 here. So the first leg is just going to be x squared dx. Y part goes away. So that's that bottom leg. For the top leg, there's multiple ways to parameterize it, but since it's nice and circular, it makes sense to use radial coordinates. Not new coordinates, you just say radius of that circle is 2, just make it go, yeah, this is basically radial coordinates. So x is 2 cosine t, y is 2 sine t. And let t go from 0 to pi. There's r, there's dr. F, you got to make those substitutions. X squared plus y squared is going to be 2. 2 squared, which is 4. And minus 2xy, I'll get minus 8 cosine t sine t. Take their dot product, I get this. And it might look a little, you don't really need a table for this thing because you can treat cosine t like u, and then du is minus sine t. You can do it without tables. But anyway, this is the important part. There it is. In at this point, you're just taking an integral. You did the hard work of the work integral. Here's another triangle. It's very similar to the previous triangle. On 2 of the legs, they're nice and aligned with the coordinate. So on this bottom leg, y is just 1, y is 0. Leg x is 3 and dx is 0. Here's the bottom and sides. See, on this first leg, y part dy, this whole term goes to 0, and this y is just 1. X plus 2 dx, that's that whole integral, from 1 to 3. On this leg, This part goes to 0. Dx is 0, and x is just 3, so that'll be a 6. 6y minus 6, and y goes from 1 to 2. Now here we've got to do that, got to come up with a line again. It's going to go from the point 3, 2 to 1, 1. You have to do those differences, but here's the way to parameterize it. This is the case where you have to parameterize it yourself, and we need to go back a module in my course to know how to describe the equation of a line using the parametric form. Couldn't think of that name before, the parametric form. So here's that third leg. I won't go through that. One last example. This one's a kind of tricky one again, because it relies on a kind of slick parameterization, which is left up to you. But they give you the R. Well, R is always X, Y, Z. And it says, here's the vector field. And here's the path. It's a straight line from the point 1, 1, 1 to 3, 3, 3. Well, we're lucky because the easy parameterization is T, 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 and let T go from 1 to 3. Let R just be equal to T, T, T. And T goes from 1 to 3. The dr is 1, 1, 1. Now make all these substitutions. All of X, Y, and Z are all T. X, Y, Z becomes T, T, T. This guy becomes that. By the way, this magnitude, the magnitude of a vector is the RSS, the Pythagorean theorem, root sum squared. It's going to be x squared plus y squared plus z squared, the square root of that. Raising that to 3 means to the 3/2 power. That's how we got that. So at this point, all we're really doing is a little bit of algebra to simplify it. So here's what F is. Here's what dr is. And now we take the dot product. 1, 1, 1 dotted with 1, 1, 1 is just what? 3. So here's the integrand. Integral we need to take. The rest is algebraic simplification, okay? The trick to this problem was knowing to do that. If you didn't do that, you would have had a fair amount of trouble with this problem. Anyway, that's all the normal way to do a work integral. In the future, there's some other methods like path independence, Green's theorem, and other stuff to help do work integrals, and we'll just cover them in subsequent videos.